In this video we'll talk about properties of electromagnetic waves, but we'll start out talking about some quick review on electric fields. So focus on the electro part of it first. So we know that if I have two charged particles at a certain distance, there's a force between them. It's dependent on the magnitude of the charges, the directionality is to each other or away from each other, depending on if they're the same sign, then they will repel. If they're opposite signs, they'll attract. Dependent on permittivity of free space and the distance squared between them. And there's a term we call electric field, which is this force divided by a test charge magnitude, so just taking that out. And so if I just have a singular charge now, there's a field around it, and if it's positive then the field lines go away from it, if it's negative the field lines towards it. At any point in space, even in a vacuum, there's an electric field. It's given by this relationship. And so we know that it's a real thing, that even though there's a vacuum here and there's just a singular charge there, that at any spot there's an electric field. And this kind of showed this spot right here. Here's this electric field going away from it because this charge is positive. So we know that's something that's real. It has no mass. It has, but can it get effect? If you put a charge there, it'll make a force which will attract and repel it. So it's a real element there. And then we know for magnetics, for example, if I have a magnet here, that there's a real thing called a magnetic field. That it goes from the North Pole to the South Pole. At any point in space, there will be a direction and a magnitude of this magnetic real field. So even if this magnet was in a vacuum, there's this thing called a magnetic field that exists there, which so if you put some other magnetic device there, it'll affect it. And we know that there's some interaction between there. For example, if I have a magnetic field and I have a charge going through that at some velocity, that there's a force on that charge, which is given by the magnitude of the charge itself, the velocity it's going through, cross the magnetic field. We've kind of already known that I can convert the force to an electric field by just dividing by the test charge. So let's say there was a test charge going through there. My electric field would be the velocity of this particle cross the magnetic field. And we can move this around. We can see that the velocity of electromagnetic wave is related to this. It's the magnitude of the electric field divided by the magnitude of the magnetic field. Imagine we have an electric charge which is moving down, and so time 1 is here, time 2 it's there, and it's kind of oscillating back and forth to these positions within the plane of the board. So this electric field magnitude and direction is changing with time, but it's in the plane of this board, and this changing electric field gives rise to electromagnetic waves. So a static electric field doesn't create a magnetic field, but a moving electric field creates a moving magnetic field, and in turn the moving magnetic field creates the moving electric field. And so that's why we're called electromagnetic, because this moving accelerating field is creating this relationship between the electric field and the magnetic field. And so for this case, I'm moving in the plane of the board, therefore the directionality of this electromagnetic wave propagating from this moving charge, the electric field is in the plane of the board, so it's in the XY plane, and it's changing with time as it's moving, and it's inducing this magnetic field which is perpendicular to it. Okay, so the magnetic field as shown is in the XZ plane, and so these two fields are perpendicular to each other, and then this wave is moving at a velocity which is perpendicular to both the electric field and the magnetic field, and therefore it's called a transverse wave. And this wave is actually, just brought about by this electric field, but this wave actually, has properties. It contains energy. It has momentum, so it can affect the world or other objects. So it's a real thing. even though it has no rest mass. It's a wave. And the magnitude of velocity, as we learned before, is related to the ratio of the electric field divided by the magnetic field, or if I had the maximum value here versus divided by the maximum value of the magnetic field. And you can see that these are in phase. Another way you can look at it is I have a little piece of paper here. It's kind of showing the same thing. Here you can kind of see the XY plane. There's electric field, and if I kind of rotate around 90 degrees from that, now it's just there's the magnetic field. And so there's this kind of same picture, picture, and this field is moving to the right using the right hand rule. So you can always determine the direction of this transverse race by taking E cross the B, and we learned that kind of right hand rules is always helpful. B, beta, the second letter, we know that the second letter is the second term, and so if I do E cross B, I show my velocities to the right, as shown right here. And then Mr. Maxwell showed us that, as you'd expect, the velocity of this electromagnetic wave is related to the electric field and the magnetic field, so therefore turns out that it makes lots of sense that it's related to 1 over the square root of the permeability of whatever material is going through times the permeability of whatever material is going through. And in the case where it's going through free space or a vacuum, this permittivity would be permittivity of free space, permeability with the permeability of free space. These are both the smallest numbers that would ever be. So therefore, this speed of light is the highest velocity this wave can ever go. And if it goes through any other media which has a higher permittivity or a higher permeability, then the ratio of these would give us the how much the ratio of the speed of this electromagnetic wave, regardless of the frequency in that media, compared to what that velocity would be in a vacuum or free space. So what are some properties of this electromagnetic wave? One would be its velocity, which we learned is the ratio of the magnitude of the electric field divided by the magnitude of the magnetic field, which is also given by this, the permittivity and the permeability of the material that's going through. So therefore velocity is really dependent a lot on, more than anything, on the media that it's going through. And then frequency. Frequency is probably the most critical thing that the frequency stays with this electromagnetic wave regardless of what media it goes through. So that's probably that's one of the true properties of this field. So when I'm creating this field, let's say I had this charge moving down, whatever frequency was going up and down with, that's the frequency that's coming out of, that's the frequency in cycles per second, how long it takes to complete a full cycle. That's the frequency of this wave going through a vacuum. That's the frequency of going through any media, going through water, going through air. That frequency just stays with it. So that's a really strong property of a wave, is this frequency. We also know that velocity is equal to the frequency times the wavelength. For frequency is cycles per second, wave is meters per second, so cycles cross out, I end up with meters per second velocity. And so this wavelength is the time for complete a full period. If it's in a vacuum, the wavelength will be longer because the velocity is c, which is the highest velocity. If I go through some media like water or air, then the velocity changes, the frequency stays the same, so the wavelength shrinks. So that's kind of a velocity frequency related term. Another property is the energy, power, or intensity of this wave. And power is the energy per time. Intensity is the power per area. For example, if I had the YZ plane that this wave is going through, it had waves going through that plane that had a height and a width, there's a certain area, and so the intensity is how much power goes through that area. And all these are related to the magnitudes of the electric field and the magnetic field. So it turns out to be the product of those two terms. So if I have a case where I have an initial wave going through there, then I have another one which has twice the electric field and twice the magnetic field magnitude, then the energy power intensity would be 4 times for that second wave compared to the first. And since we know that electric field and the magnetic field are related to the velocity, there's a way to convert, to get the product of E times B. It can be also related just in terms of the electric field squared or the magnetic field squared. Now, depending on the frequency that this accelerating electric charge is going at determines what's the frequency of this wave that's emitted from it. And there's a whole spectrum of waves going from the very lower frequencies, for example, radio waves from 100 to 10 to the 8th, and then little higher frequency microwaves, and then infrared are again higher frequencies, and then there's a whole spectrum which we're very acutely aware of because it's what we see as humans, what our eyes pick up for called visible light. There's nothing really special about it other than we happen to pick it up with our eyes, and so we're acutely aware of the frequencies of red, of the whole spectrum of the color. When we see, for example, we see the rainbow, and again, it's a lot of people kind of think of, hey, that green might be so many, the wavelength. It might be 500 nanometers, but truly that's not the way to think about it. It's more to think about the frequency than the wavelength, because independent of the media, so if you have something emitting and is emitting something at the frequency of a green wave, that if it's going through a vacuum or air or water, that frequency is staying the same, whereas the wavelength is changing. So when we think of maybe 500 nanometers associated with a green light, we're really thinking of that in air. And so that's not the best way to think about it. It's better to think about that, for example, a red light is 4 times 10 to the 14th, or to something like the 4.8 to 10 to the 14th, or 400 to 480 terahertz. Green light would be something like 526 to 606 terahertz, and violet light would be 668 to 790 terahertz. And then as I go to even higher frequencies, then I come to ultraviolet, which has a range of frequencies, and even higher frequencies, X-rays, and gamma rays, etc. And now thinking about, is there something special about these waves? I mean, there's a whole spectrum of things. They're just different frequencies. I mean, there's not, like, a lot of people associate infrared with maybe that's related to heat or something. Well, it kind of is, because it's just waves that come out at that frequency, and you kind of think of on Earth, or most things we're familiar with our bodies or the Earth itself, they're emitting infrared waves. Well, they are, because we're at a certain temperature. We tend to be, our bodies, around 100 degrees Fahrenheit or 80 degrees Fahrenheit. Well, we have moving electric charges inside ourselves, or other things, and because we're at a certain temperature, we tend to oscillate at a certain frequency, and we emit waves that reflect the temperature we're at, for example, and that tends to be more infrared waves. I mean, something that's a higher temperature, or something that has a higher frequency of electric fields will emit something at a higher frequency. So really, there's almost, think of them as the frequency is just, there's a whole spectrum, and depending on the device, it can emit or absorb. It likes to have different frequencies that can emit or absorb, depending on the structure of it and how it relates to the frequency of this charge, and therefore the frequency of this emitted electromagnetic wave. Let's consider an electromagnetic wave which is traveling in a vacuum or free space. When it comes perpendicular to a boundary, and there's another media, for example water, on the other side, what happens to it? What happens to its speed, its wavelength, its frequency, its magnitude of electric field, and magnitude of the magnetic field? So start out, we'll have this wave, and we'll pick a wave, electromagnetic wave of 600 terahertz, or 6 times 10 to the 14th hertz. That turns out to be the frequency of green light. So it has a certain frequency in free space. When it goes to a new media, that is the only thing that doesn't change. That frequency remains the same. So in this, for example, in this new water media, the frequency still stays at 600 terahertz. That's the one common thing that changes. Everything else changes. And there's some terms that help us to understand the change. One is index of reflectivity, often given the symbol lowercase n. And what n is the ratio of the speed of any electromagnetic wave in a vacuum, which is we call the speed of light, divided by the speed of that wave in a media of that. And we know that this n always has to be greater than or equal to 1, because there's nothing that travels faster than the speed of electromagnetic wave in a vacuum. And and this often depends on the frequency. So even if I have going from vacuum to water, a gamma ray or an X-ray would have or a microwave would have a different index of reflectivity than a green light wave. So it turns out green light wave going from here to here has index of reflectivity of approximately 1.33. So that tells us the speed ratio. So I'm going higher speed, approximately 3 times 10 to the 8th meter per second in a vacuum, and then I'm going slower speed, take C divided by 1.33, puts me now at 2.2556 times 10 to the 8th meter per second. So my velocity dropped. And I know my frequency remained the same, my velocity dropped, therefore my wavelength has to drop. I was at bigger wavelength here and become a shorter wavelength here. So take this ratio of speed to frequency, I get a wavelength in a vacuum of approximately 500 nanometers, or 5 times 10 to the minus 7th meter. And then when I take that and divide it by 1.33, I now get 376 nanometers. So it's a shorter wavelength. So and in this example, we're just going to consider this wave being perpendicular. We're not worried about reflectivity or refraction for this particular example. But we will think about energy. So what probably happens to energy? So it has certain energy going through free space. Probably there's going to be some energy reflected, likely. There's going to be some transmitted, and that transmitted energy and so energy, power, intensity, whatever one we're going to consider, is proportional to the product of the electromagnetic field magnitude times the magnetic field amplitude. So since I probably have lost some of that energy, that green wave is being absorbed or reflected at this boundary, reflected at this boundary or absorbed by water as I'm going through it, I expect that my energy has dropped. So this product is probably dropped. But is that all that's happened? Well, probably not. We know that magnitude of velocity is the ratio of the magnitude of the magnetic field over the magnitude of the electric field over the magnitude of the magnetic field. And since we know this velocity here is less than the velocity here, we know that ratio has to drop. So I know that my electric field magnitude is dropped more than my magnetic field magnitude. So here, let's say coming in here, they were, I'm representing the magnitudes coming in here. Let's say just for the visual purposes, they're shown here. The ratio has changed. And this is also, just to be clear, this is just showing magnitude of this. We clearly remember that the electromagnetic field and the magnetic field are perpendicular to each other. So the magnetic field actual vectoral value would be, if the magnetic field is in the plane of the board, the magnetic field would be in the xz plane, so my velocity is going this direction. In the ideal theoretical case where the energy in the vacuum, to say there's none reflected, none absorbed, the exact same energy or power and intensity was here as there, then we know that the product of here would have to be the same on both sides. And since the velocity here was lower, the magnitude of the electric field would drop, and the magnitude of the magnetic field would increase to counteract, to make this product still be the same. But that's probably that's not a real case. That's a theoretical case. In reality, we're probably going to lose some power, intensity, or energy as I transmit to this new media. And with this loss of power, this would be the magnitude of the electric field, and the magnetic fields would look like this as described before. This self-propagating electromagnetic wave, in which the changing electric field induces a changing magnetic field, which induces a changing electric field, and it self-propagates, is often drawn as a wave here, because that's how it really behaves. And like any wave, any wave like this, it has a maximum value of electric field, a maximum value of the magnetic field, but also you can kind of think of it, at any moment of time, there truly is an instantaneous value of the electric field, an instantaneous value of the magnetic field, and then at some point in time later, these are changing. So here's at this moment in time right here, here's electric field, directionality, magnitude, and here's the magnetic field, directionality, and amplitude. But I mean, this at any moment of time, this relationship still holds to relating the magnitude of the electric field to the magnitude of the magnetic field to the velocity.